bit more on what we learned in the first lesson. What happens if we're not given a zero? What if we are given no clues as to what the zeros could potentially be? How can we find out potential zeros for our polynomial such that we can find the reduced polynomial and find the remainder of the polynomial? So there's this thing called the rational zero theorem. It says that if we put our polynomial in descending order and all of our coefficients are integers, which normally they are, we can denote P over Q, where P and Q are relatively prime, having no other common factor besides -1 and 1. So if P divided by Q is a 0, then P is a factor. So let's jump into that. So let's say I have the functions, or the polynomial 3x to the fourth minus 11x cubed plus 10x minus 4. It's asking us to find all the rational zeros and then all the other zeros, and then solve for our function, and then factor it into its linear factors. So we first look at our polynomial function. I see it's written in descending order. I know that looking at that degree of 4 here, that I'm going to have at most 4 distinct zeros, which some of them may be complex, so keep that in mind. So here are the ways at which I can find the potential zeros of this polynomial. I'm going to look at the coefficient of my first term, 3. This is going to be my Q value, and I'm also going to look at 4. It doesn't matter that it's negative or positive. This is going to be my P value. So all the possibilities for P, when I look at the factors of 4 are 1, 2, and 4. And factors of Q of 3 are 1 and 3. So all possibilities of the positive and negative values of them could be possibilities for zeros. So I'm going to first start by going 1 over 1, which is positive 1. 1 over negative 1 is negative 1. 2 over 1, negative 2 over 1. 4 over 1, negative 4 over 1. And I'm going to go through the list now and do everything with the denominator of 3. Positive 1/3, negative 1/3. Positive 2/3, negative 2/3. Positive 4/3, negative 4/3. So all of these are possibilities for zeros. So thank goodness we know how to use synthetic division, and we're just going to start from left to right and see if we can't find a reduced polynomial. I prefer starting with the whole number values and then working my way into the fractions, but you can do in any order. So let's start with the number 1. So I'm going to bring down 3. I have it written in descending order. Notice that I was missing the x squared portion, so we're going to put in a 0 for x squared. I'm going to bring down the 3. 1 times 3 is 3. Negative 11 plus 3 is negative 8. 1 times negative 8 is negative 8. 0 minus 8 is negative 8. 1 times negative 8, still negative 8. 10 minus 8 is 2. 1 times 2 is 2. But negative 4 plus 2 is negative 2. Well, since we didn't get a 0, we know that 1 is not a factor. So it's not going to be a 0. Let's go continue moving on. So let's find negative 1. Let's see if negative 1 works. So I have the same synthetic division set up. I bring down the 3. Negative 1 times 3 is negative 3, giving me negative 14 when we add. Negative 1 times negative 14 is positive, so when I add, we still have positive 14, which turns to a negative 14. When we add to negative 10, we have negative 4. Negative 1 times negative 4 is positive 4. We found a 0. So f of negative 1 is 0, so negative 1 is a 0. And now we're able to have a reduced polynomial because x plus 1 is the factor. Remember, currently we have x equals -1. So when I add 1 to both sides, we now can put it into factored form. And here we have 0 x's, x squared, x to the third power. We now have our reduced polynomial. We have our reduced polynomial, and it's written in 4 terms. But we have to see if potentially, based on the last lesson, potentially it could have a multiplicity, right? It could have -1 as more than 1. So let's make sure it doesn't have a multiplicity, or it may have a multiplicity on the next page. So I'm going to use the reduced polynomial. Because it's smaller and easier to work with. And it will continue to help us reduce as we move along. So let's see if it has a multiplicity. That's the question we're looking for. Is x plus 1, is it squared? Does it have a multiplicity of 2? So to do that, we'll use our reduced polynomial with -1 or 0 and try again. So I bring down the 3. -1 times 3 is -3. -17 when added, +17 when multiplied. 31 when added, -31 when multiplied. So since we did not get a 0, we know it does not have a multiplicity. So -1 is not a double solution or a triple solution, etc. If we were to continue on this path, synthetic division would show that 2, -2, 4, and -4 are not zeros. Okay, but let's start with 2/3, maybe 2/3, a fraction. Again, I'm using my reduced polynomial since it's a smaller polynomial. Let's bring down our 3. Again, if it helps you to do some side work, 2/3 times 3 gives me just 2. -14 plus 2 is -12. What is 2/3 times -12? Here we would have -4. And 2 times -4 is -8. 14 minus 8 is 6. 2/3 times 6 gives us 4. And -4 plus 4 is 0. We found another 0. And we also found ourselves another reduced polynomial. Or we could say it's our new reduced polynomial. So right now we have, and again this is 0 x's, x squareds, the coefficients. So I have x plus 1, and right now I tried x minus 2/3 or x equals 2/3. So when I subtract, I'll have x minus 2/3 now equals 0. Or we could write it as multiply each side by 3 and then subtract 2. So these two values are equivalent, depending upon how you want to write it. I'm okay with either one. But we do have x plus 1 as a factor that we found on the front page. We have x minus 2/3 as a factor, which we just found. And now we have a new reduced polynomial as 3x squared minus 12x plus 6. What we could do is we see that they're all divisible by 3. So I'm going to factor out 3, which leaves me with another new reduced polynomial of x squared minus 4x plus 2. We have 2 more that we need to find. These potentially could be complex, or they could potentially have square roots to their fractions and they're not, or excuse me, decimals that are not nice fractions. So what we could do, I cannot factor this. I don't see anything that multiplies to 2 and adds to -4. So we're going to use the quadratic formula to continue factoring so that we can find the other zeros. Okay. So our A value is 1, our B value is -4, and our C value is 2. So x equals opposite of B plus or minus the square root of b squared minus 4 times A times C all over 2A. This gives me now +4 plus or minus, here we have 16 minus 8, or 8 when we subtract, all over 2. 8 is the same as 4 times 2, and I can take the square root of 4, which gives me 2 square root 2. I notice that all of these are divisible by 2, so when I divide them by 2, we get 2 plus or minus the square root of 2. So the rational zeros that we have found are -1, 2/3, 2 plus square root 2, and 2 minus square root 2. We have found the 4 zeros because we're looking for 4 of them. So we have found our solutions. So this is part A. We found all of our solutions. Now we want to write our solutions as an expanded polynomial by writing them in their factored form. And that's what the top of the next page will be, writing them in the factored form. Okay. So we started out, we already have the x plus 1, right? We also have 3x minus 2. Remember how I had x equals 2/3 when I multiply both sides by 3 and then subtract 2. Either one of these are okay, but this one probably looks more what we're used to. We also have x is equal to 2 minus the square root of 2 and x equal to 2 plus the square root of 2. These are kind of all together. So I would need to subtract that whole thing and subtract this whole thing and bringing it to the left-hand side, which is how I'm getting x minus 2 minus square root 2 and x minus 2 plus the square root of 2. You could certainly distribute that negative, but it's better to leave it in its whole form. All right, let's practice another one here. 2x to the 5th minus x to the 4th minus 4x cubed plus 2x squared minus 30x plus 15. It's written in descending order. We know that we need to find 5 solutions because our highest power is 5. But what are the potential solutions that we have? So I'm going to look at 2 is my p-value. So factors of, this is my q-value. 2 is my q-value. So factors for 2 are +1, +2, and factors of 15 are 1, 3, 5, and 15. Those are all numbers that evenly divide into 15 and all numbers that evenly divide into 2. We're going to have a lot of possibilities. We're going to have the possibility of positive and negative 1/1, positive negative of 3, positive and negative of 5, and positive and negative of 15. When we divide them by 1, we still get whole numbers. We also have the possibilities of taking those values and then dividing by 2. So positive and negative 1/2, positive and negative 3/2, positive and negative 5/2, and positive and negative 15/2. Those are a lot of possibilities. I'm going to suggest that you use Desmos to help narrow these down so that you can narrow down your reduced polynomial more quickly. So again, I'm going to say you can certainly guess and go through the line. It will take time. I'm going to say use Desmos to narrow down your search. Because what's going to happen is that you're going to spend most of your time guessing these possibilities versus actually once you find the reduced polynomial, then things go pretty quickly after that. But for the sake of practicing and trying things out, I'm going to start out with positive 1. I have my coefficients here written. So 2, -1, -4, 2, -30, and 15. So I'm going to bring down 1. 1 times 2 is 2. When I add positive 1, multiply, I get positive 1, add -3, multiply -3, add -1, multiply, we get -1, adding, we get -31, multiplying -31, so I get -16. Right off the bat, I know that 1 is not a 0 because it's not equal to 0 itself. So let's try -1. So I bring down the 2, multiply, we get -2, adds -3, multiply positive 3, add -1, multiply positive 1, add positive 3, multiply -3, add, we get -33, multiply, again we have 48, so -1 is not a solution. Then they're going to start working at halves and our fraction pieces. Bring down 2. 2 times half is 1. This would give me a 0. 0 when we multiply. -4 times 0 is -4. Half of -4 is -2. Add a 0. Bring over the 0 when we multiply. Half of -30. Oh, we found a 0. And if I were to graph this, I would see that 0.5 is a 0 on my graph. Okay. Go to the next page. So since f of half is a 0, we know that half is a 0 of the function, and then we can find the reduced polynomial. Looking on the previous page, our reduced polynomial will have 0x squared, x cubed, x to the 4th. So notice I don't have any x cubes and I don't have any x's. So I'll have 2x to the 4th minus 4x squared minus 30 as my reduced polynomial. Okay. So my reduced polynomial again is 2x to the 4th minus 4x squared minus 30. Notice that they're all divisible by 2, providing me with x to the 4th minus 2x squared minus 15. Perhaps we could factor this, because factoring is certainly faster than trying to guess many different options that are available. So we can multiply to -15 and add to -2, which looks like -5 times 3. So its factored form will be x squared minus 5 and x squared plus 3. Notice if I were to distribute, x squared times x squared gives me my x to the 4th. X squared times 3 would give me my positive 3x squared minus 5x squared minus 15. So that when I combine like terms, I'd get the x squared in the middle. Now we have our factored form pieces here. I have x, and we can find the rest of them. We have x minus half is 0, x squared minus 5 is 0, and x squared plus 3 is 0. When I solve, I see that x is equal to half, which we already found. Here I need to take the square root of 5, and the square root of 5 is positive or negative square root 5. And here when I subtract 3, I'll have positive or negative square root I square root 3 to get rid of that negative value. So the zeros are half, and our others are positive square root 5, negative square root 5, positive square root 3i, and negative square root 3i. We can now put this in our factored form. So if I had x is equal to half, we could multiply both sides by 2 and then subtract 1. So I'd have 2x minus 1 Right now I also have x equals square root 5 and x equals negative square root 5. So if I add square root 5 and subtract square root 5 to set them equal to 0, and same thing here, I have x is equal to square root 3i, x is equal to negative square root 3i, so x plus the square root of 3i and x minus the square root of 3i. So now we have it in factored form. The last part of this lesson is going to focus on Descartes' rule of signs. So let's say we have a polynomial written in descending order, and it has real coefficients and a non-zero constant term. So we have to have a constant term at the end. The number of positive real zeros potentially could be the same as the number of variations in sign of the polynomial, or less than the number of variations in signs by a positive even integer. We can also find the number of negative real zeros as the same number of variations when we have the opposite of the polynomial. So when we take negative x and plug into our x value and evaluate, how do our signs change? Or less than the number of variations when we substitute negative x and simplify it by a positive even integer. A zero of multiplicity m must be counted that many times. So that's a lot going on there. So let's just look at the polynomial. We'll explain as we go. We have a polynomial written in descending order. It has all real coefficients, and at the end we have a positive 4, so it's a non-zero constant at the end. How many times does our sign change? Well, here we go from a positive to a negative, so our sign changes one time so far. We go from a negative to a positive, so it's changed 2 times now, but then it stays positive, so it changed twice. We'll go to our next slide here. So we saw that there were 2 variations in sign. And that's all it asked us to do, is how many variations did it change? Let's go a step further. Let's say we have this given function 2x to the 5th minus 5x squared minus 3x plus 6. What can Descartes' rule of sign tell us about the number of positive and the number of negative real zeros? So let's first start looking at how many times our signs change based on what we just practiced. So we start with a positive to a negative. So here it changes 1 time. It stays negative, but then it goes from negative to positive. So here it changed twice. We know that items come in pair of 2s, right? So the number of positive real numbers could be 2, or when we subtract multiples of 2, or we could have 0 real positive numbers. So we know, according to this, the number of total zeros we should have are 5. And we can have 2 positive real ones or 0 when we're subtracting multiples of 2, because we know things usually come in pairs, especially if they're in imaginary values or radicals. We know that they always are coming in conjugate pairs. Now we need to determine the negative one. So we're going to substitute in wherever we see x with negative x and then simplify. I know that negative x to the 5th power is going to provide me with a negative value. Negative x squared will still be positive, so we're still going to have a negative 5x squared. Negative 3 times negative x now becomes positive 3x plus 6. Now let's see how many times our sign changes. So we start with negative and we stay negative, so our sign did not change. But we went from a negative to a positive, so it changed 1 time. And then it stayed positive. So our variation of signs is 1. Well, since we can't subtract 2 from 1 without going negative, we can't have negative zeros. That would be silly. That doesn't make any sense. So our only option is there is 1 negative real zero, and then to fill in the table. So this is this or this. We're either going to have 1 negative or 1 negative to fill in the table. Therefore, to complete, we need a non-real. So we can expect that there will be non-real values in here. So if we have 2 positive, we know we might have 1 negative. The other 2 must be non-real. So when I add these together, that would give me a total of 5 zeros. If we had 0 positive ones, which is a potential, we knew we had 1 negative based on the negative sign here. Then the other 4 to add to 5 would have to be non-real. So those are the 2 options of the 2 types of zeros that we may be looking for. Let's try another example here. Given the function 5x to the 4th minus 3x cubed plus 7x squared minus 12x plus 4, what does the sign tell us? Well, we know we're looking for a total of 4. Let's look at the variations of signs. Here I change 1 time, twice, 3, 4 times I change. So my variations are 4. So I could have 4. If I subtract a multiple of 2, I also could have 2. Or when I subtract 2 more, I could have 0. So I could have 4 positives, 2 positives, or essentially 0 positives. Let's plug in negative x and simplify and see what the variations are. Negative x to the 4th would turn into a positive. Negative x cubed is a negative, but a negative times a negative is a positive. Negative x squared is a positive times a positive, still a positive. Negative 12 times negative x is positive 12x, and 4 is still positive. Notice that we stay positive, so there's no variations. So thus there are no negative real zeros. So across the board, there are none. We can then use that information to help us fill in how many non-real or complex that we should have, because each one of these columns needs to add to 4. So if I have 4 positive real numbers, I can expect there to be no non-real. If I have 2 positives, we know that there's 0 negatives. The other 2 would have to be non-real. And finally, if I had no positives, I know there's no negatives. The other 4 must be all non-real. Let's try one more here. We have 6x to the 6th minus 2x to the 2nd minus 5x. Here we know that we're in descending order, and we're only changing our sign 1 time. We're changing our sign 1 time. So what does that tell us? Oh, but notice, when I look at my function here, they're all divisible by x. So they're all divisible by x. When I divide everything by x here, we know that x is a 0 because we would set each factored part equal to 0, so x would have to be equal to 0. So we can expect 0 to be a 0 of itself. But anyways, it still has a variation of 1, which we found on the previous page. So from here to here, or from here to here. So when I'm filling in my table, 0 is a 0 1 time, and we know we're building to 6. We know that there is 1 positive real number. And then let's look at the negative value. So if I substitute everything with negative x into my reduced polynomial here, notice I'm using my reduced polynomial. Negative x to the 5th is a negative value because we would end up with negative 6x to the 5th. Negative x times negative 2 turns into a positive, and the negative 5 stays the same. So we have 1 change, 2 changes. So it varies twice. Or subtract multiple of 2 or 0. So we could have 2 or 0. 1 as a 0 for 0 is still the same, and we would still have 1 positive because that's our only option. We cannot subtract 2 from 1, a multiple. we would go into the negative. So we'll just keep it the same. We then can find the non-real. Knowing that we're adding to 6, we can subtract. If we have 1 0 as a 0, 1 positive, so there's 4, minus 2 for the negatives would leave us with 2 non-real. And then similarly, the other column here, we would have for sure 1 0 as a 0, 1 positive real 0. If we had 0 negative real numbers, then we would end up with 4. So as a wrap up, make sure that you're using Desmos to help you to find the whole number or whole rational zeros as you solve algebraically.